Hello, my name is Eric Baldwin, and I did the modeling and control design of a DC motor. In 1834, Thomas Davenport of Vermont developed the first real electric motor, real meaning powerful enough to do a task. Although Joseph Henry and Michael Faraday created early motion devices using electromagnetic fields, the early motors created spinning discs or levers that rocked back and forth. These devices could not do any work for humankind, but were important for leading the way to better motors in the future. Davenport's various motors were able to run a model trolley on a circular track and other tasks. The trolley later turned out to be the first important application of electric power. Rudimentary full-size electric trolleys were finally built 30 years after Davenport's death in the 1850s. Okay, this is how a direct current motor works. Let's first start with the simplest DC motor possible. It looks like the one shown in the figure. The stator is a permanent magnet and provides a constant magnetic field. The armature, which is a rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it, according to the Lorentz law. So the coil will start to rotate. The force induced due to the electromagnetic induction is shown using red arrows. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. This is the system model of the open loop before the PID controller was introduced. This is the open loop step response. It is important to note that the step input is applied at time t equal to 1 instead of t equal to 0. Upon magnification of this response near time equal to 1, it becomes obvious that at the second system's response is identical to the second order system's response, 0 for some time, and rises exponentially afterward for a short time, as in the figure, and then it becomes linearly increasing. This is the system model of the closed loop after the PID controller was introduced. This is the closed loop response before auto-tuning. Closed the loop response of the system using a pre-designed PID controller and feed forward path. The response showed high overshooting before auto-tuning of the PID. And this is after auto-tuning. From the figure, it can be seen that percent overshoot is about 12%, and the settling time is about 30 milliseconds. Determine values for auto-tuned using MATLAB Simulink for better performance results, such as lower overshoot and faster settling time. The design values were as follows. And here are my reference, and that concludes my presentation. Thank you for watching.